Have you ever wondered why some reactions happen instantly while others take time? Welcome to the fascinating world of chemical kinetics and stability. This intriguing realm of chemistry unravels the secrets behind the pace of chemical reactions and the stability of compounds. It's a bit like cooking, where ingredients mix at different rates to create the perfect dish. Only here, our ingredients are atoms and molecules. By understanding these concepts, we can predict how quickly a reaction will occur or how long a compound will remain stable. This knowledge is invaluable in many fields, from pharmaceuticals, where it helps determine the shelf life of drugs, to environmental science, where it aids in understanding the rate of pollutant degradation. As we delve deeper, we'll explore fascinating concepts like half-life, energy of activation, and the Arrhenius factor. So buckle up as we dive deep into the world of chemical kinetics and stability. Imagine a radioactive substance decaying over time. Can we predict when half of it will remain? Yes, we can, thanks to the concept of half-life. So what exactly is half-life? It's a term you may have heard in various contexts, from video games to nuclear physics, but let's break it down in simple terms. Half-life is the time it takes for half the atoms in a radioactive substance to decay, or in other words, to transform into another substance. Now, why is this concept so important? Well, it allows scientists to make predictions about radioactive substances. For example, knowing the half-life of a radioactive isotope can help scientists determine how old ancient artifacts are, or how long a radioactive waste will remain hazardous. But how do we calculate half-life? It's not as complicated as it might sound. The half-life of a substance is calculated by observing the rate at which it decays over time. If a substance has a half-life of 1 hour, this means that after 1 hour, half of the original substance will have decayed. Let's take an everyday example to make this clearer. Imagine you have a bag of popcorn. You start eating the popcorn at a constant rate. If it takes you 2 minutes to eat half the bag, then the half-life of the popcorn in this scenario is 2 minutes. After another 2 minutes, half of the remaining popcorn will be gone, and so on. In the same way, a radioactive substance with a half-life of, say, 4 years would have half of its atoms decayed after 4 years. After another 4 years, half of the remaining atoms would decay, and so on. So the concept of half-life is not just about nuclear decay or video games, it's a fundamental concept in science that helps us understand and predict how substances change over time. So, next time you hear about half-life, you'll know it's not just about video games or nuclear decay. Ever check the best before date on your food package? That's all about shelf life. Shelf life is the recommended period for which products remain stable and maintain their quality under specified conditions. It's not just a date stamped on your yogurt or your favorite snack. It's a prediction of the amount of time that food, drink, medicine, chemicals, or any other perishables will stay at its best quality. But how do we determine the shelf life of a product? Well, it's a complex process that involves understanding the rate at which a product degrades under certain conditions. This includes temperature, light, humidity, and other environmental factors. The product is tested under these conditions, and based on the results, a shelf life is assigned. Now let's talk a bit about chemical stability. It's closely linked to shelf life. When we say a product is chemically stable, we mean it maintains its characteristics and functionality over time. If a product isn't chemically stable, it can degrade, change its properties, or even become harmful. So the shelf life of a product is a reflection of its chemical stability. So why is shelf life so important? Well, it's not just about avoiding that unpleasant taste when you bite into an expired snack. It's about safety and efficacy. For food and drink, an expired shelf life could mean the growth of harmful bacteria or a loss of nutritional value. For medicines, it could mean reduced effectiveness or even potential harm. Shelf life is also crucial for manufacturers and retailers to manage inventory and prevent waste. In the realm of chemistry, shelf life is a fascinating subject. It's a blend of chemical kinetics, which is the study of the rates of chemical processes, and stability studies. It's about understanding how and why things degrade over time and how we can prevent or slow down this process. So shelf life isn't just a date on your food package, it's a whole science in itself. Why does heating up a reaction make it go faster? The answer lies in the energy of activation and the Arrhenius factor. Let's dive into the fascinating world of chemistry to understand these concepts. Imagine you're at the top of a hill with a skateboard. To start rolling down, you need to push off, right? That initial push is like the energy of activation in a chemical reaction. It's the minimum amount of energy needed to initiate the reaction. Without this initial push, the atoms or molecules won't have enough energy to break their existing bonds and form new ones. Now let's talk about the Arrhenius factor. This factor is a measure of the number of molecules that have energy equal to or greater than the energy of activation at a given temperature. It's named after the Swedish scientist Svante Arrhenius, who proposed the concept. Picture this. You're at a crowded party, and you're trying to reach a friend on the other side of the room. The more people there are, the higher the temperature, the more likely you are to bump into someone, a molecule with enough energy to react. These two factors play a crucial role in determining reaction rates. The energy of activation serves as the gatekeeper, deciding which reactions can occur. The higher the energy of activation, the fewer molecules have enough energy to react, and thus, the slower the reaction. On the other hand, lower activation energy means more molecules can participate, leading to a faster reaction. The Arrhenius factor then steps in to decide how many molecules are ready to react at a given temperature. A higher Arrhenius factor means more molecules have enough energy to react, speeding up the reaction. Conversely, a lower Arrhenius factor slows things down. So what happens when we heat a reaction? Heating increases the temperature, which boosts the Arrhenius factor. More molecules have enough energy to meet the activation energy requirement, and the reaction rate increases. It's like adding more skateboarders to the top of the hill. The chances of someone rolling down increases. This is why your food cooks faster at higher temperatures, why certain explosives need to be ignited, and why enzymes, nature's catalysts, are so essential. They all involve manipulating the energy of activation and the Arrhenius factor to control reaction rates. So the next time you're cooking dinner or watching a fireworks show, remember the energy of activation and the Arrhenius factor. These fundamental concepts of chemistry are at play, determining how quickly reactions proceed. Remember, every reaction needs that initial push, the energy of activation, to get started. We've journeyed through half-life, shelf life, and even jumped over energy barriers. Let's take a moment to recap. We started off by exploring the fascinating world of chemical kinetics and stability, a field that unearths the mysteries behind how and why chemical reactions occur. We learned that chemical kinetics is all about the speed of reactions, while stability gives us insights into the endurance of chemicals under various conditions. From there, we delved into the concept of half-life, a term that tells us the time it takes for half the quantity of a reactant to be consumed. We found that it doesn't matter how much of the reactant we start with, the half-life remains the same. This concept is not just for nuclear physics, it's equally important in chemistry, especially when it comes to understanding reaction rates. Next, we moved on to shelf life. We unpacked how it's a vital measurement for everything from food to pharmaceuticals, indicating how long these items can be stored before they're no longer effective or safe to use. We discovered that it's all about stability and the rate of degradation, which is closely linked to the conditions of storage. Then, we jumped into the world of energy barriers with the activation energy and the Arrhenius factor. We learned that the energy of activation is the minimum energy required to start a chemical reaction. The Arrhenius factor, on the other hand, helped us understand how temperature influences the rate of reaction. As temperature increases, so does the number of molecules with energy equal to or greater than the activation energy, leading to a faster reaction rate. In conclusion, these concepts are fundamental for anyone interested in the vast realm of chemistry. They offer essential insights into how chemicals react, change, and degrade over time, and the conditions that affect these processes. And that wraps up our deep dive into chemical kinetics and stability. Subscribe for more because you won't find me later.